14.9, electronegativity, structure, and acid-base properties. And I'll talk about a little bit about polyprotic acids. These are problems that came from an old textbook. They might be some of the same ones in your textbook now too, but 85, 86, 87, 88. Now, you'll like this. There's not any math. I used to teach math of polyprotic acids, but they stopped doing that on the AP, so I just don't even want to confuse you with it. When I give the answer keys, maybe I'll give you the answer key if you would like to see how do you do equilibrium for polyprotic acids. I'll show you how that works. Because, like, for example, I'll just say this bit. Like, H3PO4 is a polyprotic acid. What it means is the first time that it dissociates, it gives you H plus and H2PO4 negative 1. Then the next time it dissociates, that breaks down into H plus and HPO4 negative 2. Then the last time it dissociates, HPO4 negative 2 breaks down into H plus and phosphate. Well, all of these have different Ka values. They each one, a 1, 2, and a 3. And, well, anyway, that's all I'm going to really say about that. I will say that you can also add this as a system of equations. And you could say, well, H3PO4 could break down into 3H plus and PO4 negative 3. So this has a K, that has a K, we'll call it K2. That has a K, all right, Ka1, Ka2, Ka3. Well, the overall K, you might remember, you'd multiply K1 times K2 times K3. That's probably not a bad thing just to know that. If I multiply these, whatever the number values are, this times this times this will give you the overall K if you treat it as one giant dissociation problem. But it's not that easy. I mean, it's not, and they don't even involve this, so that's all I want you to know. I think it's good to know what a polyprotic acid is. So most of what I'm going to show you is going to be, these are questions like, which one is stronger acid, which one dissociates, a range from greater to stronger acid or greater to stronger base. So all those worksheets that I've given you, like the one I did on the last lesson about conjugates, I said, oh, you can look at those later on. Well, think about that. This lesson will probably be a little shorter, and there's no math. So when you do it, you might also go back and try to do those other problems. I mean, you already turned it in, or I don't have to check it again, but you'll get the answer key to all of these. But you want to be able to do this stuff like a range from weakest to strongest, that kind of thing. And okay, here we go. So in your notes, this is actually, there's a section on this 14.9 in your notes. And when you go through it and you read it, because when I made it, I told you once before, I pretty much just took information that was in the textbook and I just like kind of summarized it. And it's like a lot of stuff. You're like, if you read this, you'd be thinking, wow, I got to memorize all this. What's the stronger acid and base and electronegativity and all this? Well, I'm going to show you some little shortcut secrets that will help you. Yes, you have to memorize some stuff, but you've already memorized some stuff. In fact, you probably already know something, and I'm going to just unlock these mysteries for what you already know here. I'll show you how it works. All right, first, there's a section here that says acidic versus basic oxides. And there's a question that said, identify if this oxide is an acidic, will cause acidic water to be produced or basic water to be produced. Well, guess what? You've seen these before. These are Mob-Noah or Lewis reactions. Okay, so the first thing, and this is kind of a review on equations, it says, what if I have SO2 and I were to put it in SO2 gas into water? Now, this is a non-metal oxide in water. In fact, you might remember, well, I'll just do it for you, show you. If you tried to do this, you say, well, it's not a double replacement. If I bubble SO2 into water, S, you think, well, S go with, it can't go with O, because it'll still be SO, or O to H will still be OH. You get the same thing. SH and OO, that's not going to happen, okay? So you just add them together. You add the letters. You get H2, and then SO3. Aha! And guess what you just made? That is an acid. So what happens is, now, does this make the water acidic? Well, bubbling that in, that one reaction doesn't really make it acidic, but then the very next moment, now this is a strong or a weak acid. It's a weak acid. So you won't get a whole lot, but you will get some H+. And you get, H+, and you get HSO3. Here's a polyprotic, and I didn't even know, I put one right there. The first H will come off easily first, okay? But it's still a weak acid. Doesn't matter. The point is it's acidic. So this is going to be acidic because that's going to decompose. All right. So we did this little thing earlier in the year, and someone once made up NOAA. Non-metal oxides make acids in water. In water. Well, in water, in H2O, non-metal oxides form acids. That's probably a better way. Okay, so there's another example on your paper, SO3 and H2O, and that one gives you H2SO4. I mean, of course, if you add all the letters SO4H2, hopefully SO4H2. Just remember, if you kind of know ahead of time, it's going to be an acid. Put the H first, and then rearrange it, H2SO4. Oh yeah, that's sulfuric acid. And of course, it's also going to immediately break down. And like I said, the first H comes off very strong acid for that one. Okay? And it'd be SO4 negative. Well, HSO4 negative 1. You know, if you had to write that dissociation, if you wrote two H's plus SO4 negative 2, you'll still get credit. Okay? But it's better to write this way because the first one is really what is a strong acid decomposition of that. Okay, so, or dissociation, I should say. All right, yeah, not decomposition, dissociation. So that non-metal oxides, any non-metal oxide. So carbon dioxide, think about that. You blow carbon dioxide into water, you make the water acidic. You make H2CO3 carbonic acid, a little bit in there. Nitrogen, NO, nitrogen monoxide, NO2, nitrogen dioxide, NO3, anything like that, phosphorus. So it'll all make sense. A non-metal oxide, and you know where the non-metals are, right? Don't be afraid if you're like, oh no, I didn't. Remember, the non-metals are over here. I don't even have that little stairway anymore, but pretty much the non-metals are fluorine, chlorine, bromine, iodine, nitrogen, carbon, all of these, phosphorus, sulfur, selenium. A lot of these are metalloids in here. So, the metalloid oxides, I guess they also would do that too. So, all right. Now, what about metal oxides in water? Can you remember what they do? The little the statement, or the what do you call it? The mnemonic device was MOB-NOAA. MOB-NOAA. Non-metal oxide acid, metal oxide base. So let's just pick the ones on the paper: calcium oxide and potassium oxide. If you drop calcium oxide into water, you just need to know. And this could actually, what I'm showing you right now, when you take the AP exam, this could be one of the equations you have to write. They're going to make you write at least three equations. And there could be some equations, stuff like this, knowledge that would help you in a multiple choice. So in a way, it might be more than just those points. But three equations, you get to write the net ionic and balance them, and they're probably going to ask you questions about them. And if they were to give you this question, the question will be, is it going to be acidic or basic? Write the reaction, the net ionic equation for solid calcium oxide being dropped into water. Indicate where the result is, acid, base, or neutral. Okay, so anyway, if you already know it's going to make a base, then you can just add the letters CaO2H2, but the correct way to really do that is CaOH2, calcium hydroxide. So you know that hydroxide is base, OH, in water. Now, to write the net ionic, since it was a solid, I chose to use a solid for this one, so that'll be solid. That will not break up. That will not break up. None of the hydroxides will break up except for group 1 and then camel with straw on his back. So it will break up. So you get calcium and hydroxides. I'll just put 2 hydroxides there. Yeah, you have to do it that way. 2 OH negative. So that would be your net ionic. Now, you have nothing on, if anything is the same on the left and on the right, you cross it out. Remember, they're called spectators. but nothing is the same. Everything undergoes a change. This was a solid. It dissolves in water, but then the calcium is left alone. The oxide react with the with water. Oh, wait a minute. Oh no, I got it right there. I was thinking I left off something. No, I didn't. Wait, one calcium, oxygen, two oxygens, two H's, two H's. Yeah, we're good. Okay, now another way you can do this one is K2O. I might as well just show it to you. I said it will be, if you want to jump past this, you can, but K2O plus H2O, what will you get? Well, you already know that K2O is going to be KO, potassium hydroxide you're going to get. But notice it's interesting, when you add them together, you get K2, O2, H2. But then when you reduce those letters, you get KOH. Actually, you get two KOHs. And what's interesting about these Mob Noah is that if I keep my numbers consistent, like KOH, but put two of them, then that will give you the balanced equation. Let's just see if that works. Two Ks, two Ks. Two O's, two O's. Two H's and two H's. All right. And then, I didn't tell, yeah, this would also be a solid. Metal oxides are going to be solids anyway, okay? But anyway, so that is the, oh no, that is not the net on it. Because on this side, once it's wet, now it dissociates. I did it on the last one with calcium, but I didn't tell you why I was doing it. Because once you get to calcium, potassium hydroxide, you have water present, so now it's dissolved, and it dissolves in water. So 2K plus 2OH negative. All right, that's an easy little thing, I think. Tell whether or not it is going to be acidic or basic when you put it in water. The non-metal oxides. I mean, you can just know it from that way. But what they do, and the homework and what they'll do on the AP, is not now, a multiple choice might say indicate which will be acidic, A, B, C. But on a free response, they'll say actually write the equation. And that's why I want you to know how to write them. And the homework's going to have you write them. Okay. You can read the notes if you want there. But yeah, like I said, I got some shortcuts I'm going to show you. Okay. Now, the next page, it says electronegativity. Well, it might be 3 pages, 2 pages, third page over. Electronegativity and acid strength. And it says any molecule that contains hydrogen atoms could potentially be an acid, but not all molecules with hydrogens are acids. Okay, well, this is a kind of easy thing. It has to do with structure. You already should know, just from organic as well, is CH4 an acid? No, it's not, because the H cannot break off, okay? Because they're all covalent bond to the carbon. They don't come off very easily. All right, so that would not be an acid, no, okay? What about HBrO3? Yes. This is what's called an Oxy Acid. So any polyatomic ion you see with oxygen in it, you add H or 2 H's or 3 H's, whatever, like phosphate, PO4, -3. You'd have to add 3, H3, PO4. You add, anytime you see an a polyatomic ion with oxygen, that will make an acid, okay? H to it. Even if you see a polyatomic ion like that you've never seen before, but I want you to notice this, and we'll be getting into it later. You haven't seen BrO3, -1, but you have seen ClO3, -1. And notice fluorine, chlorine, bromine, iodine. You can just stick those in. That's called chlorate. So that must be bromate, and it is. Guess what? If I put an I right there, that's called iodine, iodate. And so it's the same charge. It just steps right in. That's a neat thing about it. So, but anyway, all of those polyatomic ions with oxygen, oxyanion, they will be acids. Okay, here's another one, CHCl3. No, again, it's not, because it's bonded to a carbon. So bonded to a carbon won't do it. It's organic. HCl, yes, you know that's an acid. Okay, and here's one, CH3, CH2, CH2OH. Now, that's a good one, and this is one they probably love on multiple choice, try to get you and trick you on that one. No, it would not be an acid, but also, would it be a base? Oh, it has OH. It's not a base either, because this is an alcohol. Hopefully you can kind of remember that alcohols look a lot like they're an acid or a base. Now, how would you know an organic acid? I didn't put that one on here, but I need to add that. So the main one is CH3COOH, Chaku. But what is it really happening there? Well, let me just draw it. I mean, you're like, oh boy. Because, yeah, remember, organic can certainly be on the AP. Here's what happens. You're going to have a C double bond to an O, and then you're going to have an O to an H. This is an acid. So acetic acid or vinegar, CH3CO, one of these has a double bond and one has a single bond. So this can break off, and all right, the H plus breaks off. H plus means no electrons. It leaves the electron behind. 2 electrons are there. And now this is acetate. Now, if you want to go back and review the videos for, that would break up into that right there. Well, actually, I can do that. That one breaks up into acetate and that. Okay, I didn't draw the structure, but if you want to go back and watch the organic videos again, you can see. But basically, remember this. This is called methane ethanoic acid. Methanoic acid, ethanoic acid, propanoic acid, butanoic. They might have a different number of carbon chains, HHH and all that, but they all have this at the end of it. C double bond O to OH. And the H can break off, and that's an acid, okay? I just want to tell you that. You need to know that it would be acidic. And then for that matter, why don't I just throw in what will be the basic organic one, and I've shown you that as well. So if I have COOH, if you have this, it's called a carboxyl group. If you have this attached to an organic molecule, and you can see a structure that can give you a picture, that's going to be acidic because that can break off. But if you have NH2 attracted to it, you probably remember that as well. NHH, and I'll put a lone pair there. That will be basic because it can grab an H right there and become CH3 NH3 plus. And you've seen that in this chapter. So CH3 NH2 would be a base, and then with water, it's going to take off the H and make it CH3 NH3 plus, and then it takes the H away, so you have OH negative left over. So there's your base right there. If you see NH2, if I put this in water, will it be acid or base? It will cause the water to be basic. Okay, it's an organic base. If I put something organic in water that has that on it, it will become acidic. The H will break off. Okay, that's enough of that. And I overdid it a little bit, but I wanted just to show you all those bits. Now, where are the shortcuts of the things I told you about? All right, when the bond between H and other element has low electronegativity difference, the bond is essentially non-polar. It does not break off. Okay, carbon. You don't have to worry about that so much. Now, highly polar, low polar, stronger acid, weaker acid. So here's one little thing I found in the book, and I want to show you that you know a little bit about this. Let's say that you had to compare HF, HCl, HBr, HI. Okay. All right. Well, first of all, the question could be which is stronger. Sometimes you can get confused on this. You know that they talk about electronegativity and bond strength sometimes, but let me show you what you know for sure already. What can you remember about? Tell me this. What are the 6 strong acids? You say, well, hydrochloric, hydrobromic, hydroiodic, and then nitric, sulfuric, perchloric. Notice who was left out of that? HF. Well, it turns out on the chart that the pattern matches what you see on the chart: fluorine, chlorine, bromine, iodine. Look on the periodic chart and you see this: fluorine, chlorine, bromine, iodine. If I add an H to F, HF, HCl, HBr, HI, which one of those is the weakest? Oh, HF. We talked about HF as a weak acid. The reason, you know that fluorine, well, the real reason is because it has a very, the bond strength is very, very strong. Now, you don't have to memorize this, but I want to show you it's in your notes. But notice right here, HF, it says the bond energy. To break that, you got to add 65 kilojoules. But now for HI, you only need to add 295. So 585 all the way on down, like 600 to 300 to break HI's bond, to break it apart. So why does that matter? Well, if it's an acid, is somebody that's very good, easy to give off the H plus. So it's very easy for HI to break away. That would tell you that HI is a strong acid, stronger acid, because it can easily come off the H. The bond energy is small. It holds it, but HF holds it really, really strong. So it's a weak acid because it doesn't let go of the H. But here's what that's the reason behind it. But here's something that you probably will not forget, and maybe hopefully you won't forget that too. But here's something you wouldn't forget. Which of these are strong acids? Oh yeah, the strong are HCl, HBr, HI, but that's a weak acid. Well, if that's weak, not only is it weak on the chart, it is the weakest in this series. That is the strongest. We just saw that. So you can just remember, weakest, stronger, stronger, strongest. Okay? I guess that's pretty much all I would bring up to that. Let me think about this for a minute. Yeah, it doesn't want to let go of that H. That's pretty much it. Another way to look at it, well, I better not say that right now. I want to confuse you. So just remember that that's the weakest and that's the strongest. It has to, the real reason because of bond energy. Strong bond, it's hard for the H to break off. But you can just memorize on the chart and know that, oh yeah, HF's a weak acid, so they must get stronger as you go down, and they do. They get stronger, stronger, stronger. All right, so that's easy. That's easy to remember about those four acids. So if they were just to say on a multiple choice, which is a stronger acid, H, Br, or HI? You're like, oh, wait a minute, what? HBr or HI? Well, hopefully you'll go back and remember, okay, this little pattern and say, oh yeah, HI is the strongest. And it has a really weak attraction energy, a bond energy. H is really low attraction to I, but here it's stronger. Okay, all right, that's the real reason. I don't think they would ask you to explain that, but they could, and it would be a small couple word statement. All right, now what's the next thing in the notes there? So bond energy. I talk about the polarity there. I would kind of get away from that part. I would not worry about that right now. In an oxy acid, let me just see. Well, I want to read the part about the polarity. I was saying I'm not going to read it, but now I'm thinking HCl, HO bonds, there's a great electronegativity difference. The polar bond exists. Bonding has a tendency to be pulled away from H. So H. Well, I don't. Okay. HX hydrohalic strongest. We already talked about that. Oxy. Okay. Oxy acid. That means an acid that has a polyatomic ion containing oxygen. And I told you about this already. And there's also something you know about this as well. And here's what it says in the chart. It talks about, oh, I actually did type this in for you. This is my little part of my little shortcut secret. But they could say something to you like, which is going to be a stronger acid? H, I didn't put it on here, so I'll make it up now. H, BrO3 or HiO3. Which is going to be a stronger and which one is weaker? Okay, now for oxyacids, it's interesting. I can't do the exact Lewis dot diagram for you, but I don't want to go through. You have to do the ABC method. Then you have to do formal charge also, except you won't do formal charge. Oh yeah, for fluorine you wouldn't do it, but starting with chlorine, yeah. So if the center atom, you would never do formal charge if it's like not HNO3 or if it's HF. That wouldn't matter for HF. There are no oxyacids with fluorine in it. Carbon, H2CO3, you wouldn't do it for that. They would follow the octet. But everything with these, phosphoric acid, sulfuric acid, perchlorate, chlorate, all that, they all can do formal charge. So you would do the Lewis dot diagram. You would do, then you would change by formal charge, use the ABC method, then do formal charge. Well, anyway, you're going to end up getting this, something like this. The iodine or the bromine are going to be surrounded by oxygens, and then the H will be attached to one of those oxygens. Okay. Now these might be like double whatever bonds in there. I don't remember it exactly, but we'll get it. And then this is an oxy acid. on all the oxyacids, there's only one that doesn't do it, and it's H3PO3. I believe that's the right one. Phosphorus acid. And don't worry, they're not going to ask you about that. But anyway, look, on the oxy acid, the hydrogen breaks off of and leaves behind the element with the oxygens around it. Now, the reason why that's significant is I want to show you this. A stronger acid is going to be one that when the H plus goes away, now this is going to become negative, right? And so you have to put brackets around it. It all becomes -1. The H plus leaves. Well, when the H plus leaves, whoever is better at handling that extra negative charge is going to be the stronger acid. It's more stable than negative charge. Who's going to be more stable than negative charge? The element that is more electronegative. Okay? So the center atom, the more electronegative, for an oxy acid, the more electronegative acid is going to be the one that is stronger. The more electronegative element in the middle of an oxy. Now for this, it's not the case, because don't think about it that way. Only for oxy. More electronegative will give you the stronger acid. The more electric central atom, more electronegative. Because what happens is that negative charge will be shared around oxygens, but it can get also given to I. I is better with it. Okay, so that's the deal. So just based on that alone, you'd say, okay, who's more electronegative, HBr or HI? And you say, oh yeah, Funkelbrich. And you say, well, bromine, iodine, this is the most negative, so bromine's more electronegative. So that would be the stronger acid, and that would be the weaker. It's the stronger acid because when its H leaves one of the oxygens and it leaves behind a -1 cloud charge, that -1 is better handled by 3 oxygens with a bromine than 3 oxygens with an iodine. Okay? Because electronegative is like a love for attraction for electrons. Okay, but now there's something even better that I want to show you about this. Watch this, watch this, watch this. Okay. Remember I told you, the easy way to remember who's stronger and weaker of this is just remember, hey, HF is a weak acid, but these are strong. So HF, they get stronger, stronger, stronger. Well, here's another way to remember oxyacids, and I love this, and I wrote it on the paper. This is my own little thing. Tell me about this for a moment. What do you know about HClO4? It is a, what kind of acid? Strong or weak? It is a strong acid. You know that. It's one of the 4. Okay. Do you know any other acids that have H and ClO? Yes, you have HClO3, HClO2, and hypochlorite HClO. Well, okay. Oh, I didn't want to tell you that yet. We'll look at that in a minute. Don't look at that for a minute. Forget what I said. That's going to be something else. That's another part of my secret, the mystery. Okay, here's one part of the mystery. HClO4 is a strong acid. You know that already. So let's just change that Cl to something else like Br or I. Now, there is no such thing as HF, but if there were, there is none, so they won't mess you up. All right, so let's just put HBrO4. Let's put HiO4. Tell me this. So we want to know who is the stronger acid between these 3. Well, first of all, that is a strong acid. You know that. So that is not. So that must be weaker. And it is. It's weak. And that's also weak. Well, it's based on electronegativity. So you might remember, that's the more electronegative, chlorine, in Funkelbrich, or on the chart also, remember, up and to the right. That's more electronegative, less and less. Go down less, more up more. So when this H leaves HClO4, this is very electronegative, so it's very good, very stable. That's why it's a strong acid. This one is not as stable. It's weaker, but that would be the weakest of the 3. So there it is. So sometimes they give you 2 acids that'll say HClO4 or HiO4. Or they could ask you these 2, like I just did a moment ago. HBrO3, HiO3. Maybe you can just remember that HClO4 is an oxy acid that is strong. That is strong. But if I change that middle element to anything, now it's weaker. Okay? And, well, maybe you need to know it's based on electronegativity. So that one gets weaker, and that will be the weakest of those because it's the least electronegative there of the acid. Okay, so maybe that little shortcut will help you. I mean, if it's a shortcut, HClO4 is a strong acid, so I'll always know. So then HClO4 is strong, so HBrO4 is weak. I changed that element. Same thing, if I had HClO3, well, there it is, HClO3, HBrO3, HIO3. Well, that will be the strongest now. That will be the middle, and that will be the weakest, okay? So HClO3, because it's more electronegative. But I don't want to mix you up. All right, and the last thing, the last little trend is the number of oxygens attached. Now, this is a strong acid. Is that a strong acid? No, it's not. So watch this. That is a stronger acid. That's weaker. That's even weaker. And that will be the weakest in that little group. Let me just go across there. So it's really kind of the same reason I told you before. Well, it's true. Those are electronegative. That doesn't change. But now you have less and less oxygens. See, oxygens are also very electronegative. When you leave a negative charge, when hydrogen leaves, it leaves a -1 charge on all of this. The 4 O's in Cl are great at holding that -1. They're okay. They're good with it. They're stable. But now you take away an oxygen, now that's a little bit less stable. That's a weaker acid. Take another oxygen and another. So having less oxygens means that charge can be, that negative charge is distributed less stable. It's not distributed as well, and so it's weaker. All right. And is there anything else I wanted to say? No, I think there isn't. Oh, I do have one. It said in a similar structure, oxy acid, the central atom is more electronegative, produces stronger acid. Yeah, I already told you that. Okay, that's the same thing. All right, there is one little thing about polyprotic acids, and I'll show you this last bit. Okay, now this part you're probably not going to be asked about, but it could be. I mean, I don't know. You could know a little bit about this. So I put on here H3, ASO3, H2ASO3, -1, HASO3, -2. Okay, so what is a stronger acid and what is the weaker? I think I kind of told you this already. And in fact, here's another way you could know this. When that breaks up, remember I told you first comes off H+. The first H comes off, that's a strong acid. But now that is a weak acid. Okay, so when you lose an H, it becomes weaker. It doesn't want to let go of that H as much. Okay, so the first H comes off. That will be the strongest. That'll be weaker, and that'll be the weakest of all the acids. What do I mean by weaker and weakest? The K value of this will be larger, but the Ka for this will be smallest of all of these. How about I'll put the largest, and that will be the Ka in the middle. All right, so that's pretty much all you'd have to know for that. So every time you lose an H, when you lose an H, it becomes -1, right? So now all of these want to distribute that -1 charge, and so it doesn't even want to let go of another H if it doesn't have to. It becomes harder to take off each one, so it becomes more and more attracted to it. Now, there's one other thing I could show you, and I'll just say it last of all. It's based on what I told you in an earlier lesson. And remember, if this is the strongest acid, and this is the weakest acid, then the conjugate bases of those will be the opposite. The strongest acid will have the weakest conjugate base. The weakest acid will have the strongest conjugate base. So if this is the strongest acid, what is its conjugate base going to be? Just take off one H. H2ASO3, -1. That will be the conjugate base. But for this one, the weakest acid, its conjugate base, if you take away that, will be ASO3, -3. All right, conjugate base. So think about this. The strongest acid, that's the weakest acid. The strongest acid, the conjugate base will be weakest, But this conjugate base will be the strongest. So in other words, strongest. ASO3 negative 3 is a stronger base than H2 ASO3 negative 1. You know, you would think that too, because if you put that in water, negative 3, wow, it's going to grab an H really, really quick. It doesn't want to be ASO3 negative 3. It's going to grab an H. That one, it's not going to grab it as strong. So strong acid will have the weakest conjugate base. And of course, that will be in the middle. So H, what will that be? Its conjugate, take off one H, HASO3 negative 2. So for conjugate bases, this will be the weakest. That will be stronger. That will be the strongest. That will be the middle one right there. Okay. So conjugate base means it wants to gain another one. So, all right. Well, that's all of it. That's all the wrap up of this material. You're like, what is all this stuff? It's crazy. But go over it. Do all those problems. 85, 86, 88, 87, 88. It won't take you that long. And then you might want to look back at the conjugate worksheet, the conjugate salt. Those problems, I said, you can skip them and see them later. Well, if I haven't given you the answer key yet, or even if I have, go back and look at them and study over those as well. Range from weaker to stronger, conjugate and all of that, and see if you can do all that stuff as well. I mean, on my test, it'll be like multiple choice stuff, pretty much. On the AP, it could be multiple choice, but it could also be, you never know, it could be one little like a short answer question that pops up in the middle of a big FRQ. And every little detail that you remember like this can help you on the AP. I mean, every little point can help you. If something is hard like this for you to remember on the AP, like all I'm telling you, it's hard for most anybody taking the AP to remember. Some people are super sharp, you know, they remember photographic memory, and I was not that way. I just over time. But I have to remember my little patterns here on the chart. HF, HCl, HBr, HI. HF weakest, HI strongest. Remember that. I remember HClO4 is a strong oxy acid. Anything else would have to be a weak oxy acid. HClO4 is strongest, HClO3 weaker, HClO2, HClO weaker, okay? And if I change the middle element, you know, electronegativity. Okay, I'm too much, right, going crazy. I'll see y'all later.